Chapter 2, Section 5, Key Components and Workflow of Predictive Analytics. In our machine learning analytics project, it is important to follow an appropriate workflow to conduct the analytics effectively. This slide shows the workflow and its main components. Among these components, data collection and preparation are the steps that significantly impact the performance of the machine learning model. This section provides an overview of each of these steps. The in-depth knowledge required to perform each step effectively will be covered in subsequent chapters. When we collect data for analytics, ensuring data quality is an essential issue. In data analytics, data quality is one of the most important issues. As the saying goes, garbage in, garbage out. Low-quality data does not yield useful insights. It can lead to erroneous insights and decisions. A thorough data collection and preparation process is essential to ensure data quality. Data quality issues include missing data, errors, inconsistent notation, etc. So, ensuring data quality is also a purpose in the next step, data preparation. Quality issues also include relevance. This means that data should contain features that can be useful information for our problem solving. Data lacking relevance does not provide necessary information, making the analytics meaningless. The data preparation phase includes processes such as data cleaning, data integration, and data transformation. These steps are essential to make the dataset useful for machine learning analytics. Data cleaning is the process of addressing problems such as missing values, duplicate records, and inconsistencies in a dataset. A missing value is a variable in an observation for which no values is stored. Missing values make the training of some algorithms impossible or distort the training results, so we must handle them appropriately. Techniques for handling missing values include imputation, record deletion, and using algorithms that can handle data containing missing values. In addition, other cleaning procedures such as identifying and deleting duplicate records and unifying the notation are necessary. Data integration is a process of combining data from different sources to create a unified dataset. This involves integrating data stored disparately within an organization, such as combining data on salespeople's sales activities stored by individual stores with data on salespeople held by the Human Resources Department. Data integration provides richer, more multifaceted information and promotes more effective decision-making. Data transformation is transforming raw data into a format suitable for modeling. This includes quantifying categorical variables. It also includes normalization and standardization to compare variables with widely different means and variances. Further, we can generate new features from existing features to make our dataset more informative. Once the data is ready, we select a model. Here, we choose the appropriate algorithm based on the nature of the problem we are working on and the nature of the data. Suppose we are analyzing customer data. Here, we have three problems we want to analyze. The first is to predict how much each customer will purchase in the coming year. The second is predicting whether each customer will purchase a new product. The third is to group the customers based on some characteristics. In the first two cases, the target variables are predefined. That is, how much each customer will buy next year, and the binary variable, whether or not each customer will purchase the new product. Therefore, These two are supervised learning problems. The third problem is the problem of grouping people based on some features. If it is unknown how the customer should be grouped, the problem is treated as unsupervised learning. If the task is to determine which predefined group an observation belongs to, supervised learning or other statistical methods are more appropriate. Supervised learning uses regression algorithms when the target variable is continuous, and classification algorithms when it is categorical. Thus, we should use regression for the first problem and classification for the second. In addition to the nature of the problem and the data, factors such as the size of the dataset, the complexity of the relationship in the data, and the high need for interpretability of the model will also influence the algorithm selection. These points will be discussed in more detail in subsequent chapters. Once the algorithm is selected, the model is trained. In this stage, the algorithm is applied to the dataset to build a model that has learned the patterns in the data. At this phase, the model must learn the patterns and the structures in the data, rather than simply memorizing the dataset used for training. Otherwise, the model can achieve high prediction accuracy only for the data used for training, and the prediction accuracy will be low for new unknown data. Therefore, in this phase, we can use several methods to ensure that the model performs well on new unknown data. The popular methods are hold-out method, grid search, and random search. These methods will be discussed in detail in subsequent chapters. Once the model has been trained, the performance of the model is evaluated. In model evaluation, we first evaluate the performance of the model using the data used to train the model. In the case of supervised learning, we evaluate not only the performance on the training data, but also the performance on the test data. There are a variety of model evaluation metrics. According to the method and purpose of machine learning, it is necessary to evaluate using appropriate metrics. Usually, multiple models are developed, and the model that shows the highest performance in the model evaluation is adopted for practical use. Model deployment is a process of integrating trained machine learning models into a production environment that can be accessed and used by end users and automation systems. This step involves migrating a model built in an experimental environment to a practical application. In model deployment, we must consider the system load for handling large amounts of data, computation speed, and security. Once the model is deployed, we should monitor its performance continuously. Because data becomes stale due to various changes after the model deployment, the model's ability to predict new data may deteriorate. For example, because of market trend changes, historical customer data may no longer reflect current patterns of customer consumption behavior. Therefore, we need to implement continuous monitoring of model performance, recollection of data, and retraining of models. This chapter outlined three types of machine learning: supervised learning, unsupervised learning, and reinforcement learning, explaining their characteristics and how they differ from each other. In supervised learning, models are trained on labeled data to predict outputs. Unsupervised learning uses techniques like clustering and dimensionality reduction to discover unknown patterns in unlabeled data. Reinforcement learning builds models that learn by trial and error through interaction with the environment to determine optimal behavior. This chapter also describes the key elements of a machine learning project: data collection, data preparation, model selection, model training, model evaluation, model deployment, and monitoring. Based on the above overview, subsequent chapters will go into detailed technical and theoretical explanations. Thank you for watching. Please thumbs up and subscribe to my channel.